This video will present another application of the second law of thermodynamics in an open system. Okay? You see here the picture. Okay? And there is a turbine. Okay? This is a turbine, the second law of thermodynamics, open system. This is a turbine. Okay? Here the flow, the superheated water vapor enter on this inlet of this turbine at the mean velocity V1 150 meters per second, the temperature 400 Celsius, and the pressure is 30 bar. Okay, and this superheated vapor is expanded in the process of this turbine, okay, in which the fluid loses energy. Okay, there's a work done by the fluid, okay, and the turbine, it receives the work done by the fluid is a 500 kilojoules divided by kilogram. The velocity, the exit velocity is 100 meters per second, and the temperature dropped from 400 degrees centigrade to 100 degrees centigrade. Okay, this is a saturated vapor. Okay, you can see on this figure over here. Okay, the pressure drops. Okay, from 1 to 2, and the temperature here is a 400 Kelvin, 400 degrees centigrade, and the temperature at the exit is 100 degrees. Okay, obviously we'll work with the centigrade or Kelvin, but when you work the difference, doesn't matter. Okay, for instance, if you add 273 and subtract 273, okay, when I use the difference between the temperature, doesn't matter if you use centigrade or Kelvin. But if you have a relation, for instance, T1 divided by T2, then you have to use Kelvin. Okay? Now, here's the temperature of the surrounding, okay, TB, 25 degrees centigrade, and on the table, the superheated vapor table, you find out that at the temperature 100 degrees, okay, saturated, you find H2, the enthalpy is 2676 kilojoules divided by kilogram, and the entropy at the exit at the same temperature is 7.36 kilojoules kilogram Kelvin. Okay, now at the entrance, okay, the enthalpy is 3231 kilojoules divided by kilogram, and the entropy is 6.92 kilojoules kilogram Kelvin. That's the data from the table. Okay. Now, what I want to determine the rate of entropy generation. Okay. This is lambda dot divided by m dot. Okay. This is a kilojoules kilogram Kelvin. Okay. Now I'll make some assumptions. A superheated vapor is expanded as a steady process. What means that? The derivative with respect to time, okay, is identical to 0. Okay. Now, the potential energy variation is neglected. Okay, delta, okay, potential energy variation is equal to 0. Okay, I'm not saying the potential energy is 0. I'm saying the variation of potential energy is 0. So I'll start the solution, okay, using three laws, okay? This is a continuous equation, okay? It's a conservation law of conservation of mass, and I use the first law of thermodynamics and the second law of thermodynamics to solve this problem. Okay? Let's start with the continuous equation. Okay? Now, as you know, as we did before, okay, eta is 1, okay, do you remember? Eta is 1, and this I have 0, okay, this because it's a steady process, okay. Here is rho v dot dA is equal 0. Now, if you apply to the surface, okay, of this equipment, the turbine, you have section 1 and section 2, which flows, okay, water vapor, okay. Now, then, the sign is important. The sign of rho VdA at the entrance is minus, see, minus m dot 1, okay, put here, and plus m dot 2, okay, at the exit, because the dot product at the exit is positive, because the angle between the vector v and the vector dA, in which it points out always for the surface, okay? dA is always, the direction is always towards like this, okay? Out, okay, of the surface, okay? Now, this I have minus m dot 1 plus m dot 2 is equal 0, which implies that m dot 1 is equal to m dot 2. I just use this notation here. I call them m dot, okay, to represent m dot 1 and m dot 2. Now, this is a continuous equation, okay? Now let's jump to the first law of thermodynamics. Now, from the first law, okay, the heat minus the work, I'll call, in this case, okay, Q dot actually is heat divided by time, okay, but I'll call heat and work. This is the power, okay? The dot in the work is the power, that's the power, okay? Now, Q dot minus W dot of the shaft work, okay, could be a pump, could be a turbine, okay, a fan, a compressor, okay, that we call shaft. And minus, this is a work, okay, done by the pressure, okay. Pressure acts on the surface, okay. The force due to pressure, okay, acts on the surface, okay, not on the volume. Okay, that's why you have control surface of PV dot dA. Okay, V dot dA also has a sign. Okay, now this is the work done by the pressure. Okay, and the expansion. Okay, now you see P is a force. Okay, VdA is volume divided by time. You see here, okay? You can see V, for instance, is meter per second times the area, okay? Times the area, okay? And this will be the unit. Will be meter cube divided by second. So PV, do you remember? P times V volume, okay, is a force, okay, because P is force Newton divided by area, okay. When you multiply by the volume, okay, you have Newton meter squared times, you cancel, you have meter here, Newton times meter, okay, is joule, okay? We already saw this, okay? Now, let's continue here. So, PV dot A, okay, is work divided by time, okay, this power, okay, like this term over here, the unit, okay, of this term here, this is power, and this is power, okay. Now, the second law says, the first law says that the left-hand side must be, okay, the time derivative of E total, okay, the total energy. The total energy for the open system is internal energy, intensive, all these are extensive properties, okay, depends on the mass. Kinetic energy, 1/2 of mv squared, and potential energy, okay, these are extensive properties. Now, if I divide by dm, the derivative, this is intensive, okay, this is raised here, and I wrote here, intensive properties. Okay, that's all depends on the mass. So I have a small u, internal energy. This is kinetic energy, v squared divided by 2, and this is the potential energy. So I'll plug, okay, in that famous equation, okay. The famous equation I'll repeat here, okay. dN dt of system is equal partial respect to t, okay, that's 0, plus integral of control surface eta rho v dA, okay. Now, eta is just this term over here. So if I plug here, and this I call small e t, okay? T is total, okay? T is total, right here. D is total. Now, this term over here on the left-hand side, I put in the right-hand side, okay, that to combine with the ET, okay? Now, why I did that? Because this is rho and rho here. If I multiply rho VDA times this red rho here, it will be only P VDA, which comes from the left-hand side, okay? That's why I divide by rho, and this multiplied by rho, okay? Now, I continue doing this. So, this term over here, P over rho plus the internal energy, is called enthalpy, okay? Now, enthalpy is an intensive property here, okay? Because there's a combination, okay, of these state variables, U, P, and rho. Okay, rho is 1 over V. V is the specific volume, okay? Rho is the specific mass, okay? Specific mass. And V is the opposite, the inverse, okay? Is the specific volume. The product rho V is equal 1. So it doesn't matter if I work with rho or small v, it doesn't matter, okay? Because enthalpy is, in this case, U plus PV, okay, from thermodynamics, okay? The relationship, this is the U, okay? This V here is 1 over rho, so no problem. If I write P over rho times U, okay? This is kinetic energy by unit mass. This is the potential energy times rho VDA. Now, I will apply this equation here, you see, this equation here to the system, to the fluid. Attention here, the turbine is not the system. The system is the vapor, okay, is the superheated vapor. That's the system, okay? Now, this is section 1 and section 2. I already set the sign, the section 1, okay, the sign of rho VdA, okay, the sign over here, and this is minus m dot 1, this is plus m dot 2. Then I call m dot 1 from the continuity equation, okay? This will be minus m dot plus m dot, okay? Then I rearrange this term over here. Then I have Q dot minus the power, okay, of the turbine, okay? W dot turbine. This T here is a turbine, okay? This m dot, this H2 minus H1. H2 is at section 2, obviously. This is 1/2 of the kinetic energy, okay, by unit mass, okay? All of this is by unit mass. Now, here didn't appear the variation of the potential energy. Why? Because the variation is equal to 0, okay? Now, the Q dot, now I divide both sides, okay, by the flow rate, the mass flow rate, okay? M dot is the mass flow rate, okay? I'll divide this, divide both sides, okay? This M here will be dropped from here. So I have Q dot divided by M dot. Now just numbers, so see, I have all this number over here, okay? All this number, okay? This is 500, this from the water vapor table, okay? This is, I know, because it's from the data, okay? V2 is 100 meter per second, and V1 is 150, okay? Let's show that. See, 150 and 100, okay? Then I substitute this number, this from the table, and I get Q dot divided by M dot. I just add this. Attention here, okay? This V square here is meter square by second square. Now, then I work a little bit here just for you to see, okay? 1 Newton from the Newton's second law, okay? Force is equal mass times acceleration. That's a definition of the 1 Newton, the unit of force in the international system, okay? Then this multiplied by meter here. Meter here is on joule, is Newton meter, is 1 kilo. Here is the meter square. This is the m square divided by s square, okay? So the unit of m square by s square by second square, okay, is just joule, okay? That's on the left-hand side, this is 1 joule, okay? Divided by kilogram, okay? But all this term here must be to express, okay, in kilojoule by kilogram. That's why I multiply by 10 to the power minus 3, okay? It's just over here, okay? Now, these are numbers, okay? These if I have a calculator, okay, I can do this easily. And here I have 6.31 kilojoule by kilogram, okay? Now, you see, this term over here, attention now, okay? It indicates, okay, that the system, who is the system? The system is not the turbine. The system is the flow, okay? It means that the flow is losing heat, okay? It is losing heat here. I'll put it over here. See? This is a Q dot divided by M dot, okay? This is losing, okay? The fluid losing heat. Okay? Now we are ready to apply the second law of thermodynamics. Okay, let's go. Balance of entropy is not conservation of entropy. You have conservation of mass, conservation of momentum, okay, from Newton's law. You have conservation of energy from the first law. But you don't say conservation of entropy, okay? You say balance of entropy. Now, I use always I use the relation, okay? Control volume, okay, and system, okay? This is system and control volume, okay? This is system, okay? With our subsystem, okay? I like to call this because the subsystem plus the surroundings, okay, that's a big system, okay? But I use this is the entropy, okay? That's extensive entropy. Okay, the small s, okay, is the intensive property. Intensive entropy, okay? Which S is equal ds divided by dm, okay? Doesn't depend on the mass. So this is my denotation, this is my eta, okay? This is my eta. Since the process is steady process, this is zero, okay? Derivative with respect to time is zero. So this is left, okay? And don't forget the right-hand side, okay? Now, I will expand this in the section 1 and 2, which we have flow in and flow out, okay? Carry entropy, okay, inside the system, inside the volume, through the surface, okay? This is surface, the surface here, okay, which is important. Now, I know the sign, okay, is plus or minus, I know that. In the section 1, this dot product is negative. At section 2, the dot product is positive, okay? Because the vector dA always points out of the surface, okay? We already did that. Now, you see minus m dot 1, S1, plus m dot 2, I call m dot, you see the green one here. Then I explore this a little bit, okay? I set m dot, this S2 minus S1 is equal to, attention now, the right-hand side, okay? Now you remember, you have to remember the video which I set, okay? This heat, okay, the potential, this power, okay, heat is flowing out, okay? That's why this, you see, I'll show you here. See, this is minus 6.31 kilojoule divided by kilogram, okay? Now, this minus hits here, okay? This is the minus 6.31. Why minus? Because the system is losing heat, okay? Now, divide by the temperature, the surrounding temperature, TB. This is 25 degrees centigrade plus 273, okay, to transform degrees centigrade and Kelvin. Okay, don't use degree in Kelvin. Kelvin, there is no degree, okay? Don't put like this. You put centigrade, don't put Kelvin, okay? Just write down Kelvin, okay? Now, then this is my unknown. Oh, that's good. You see, this is my unknown. That's right here, okay? This here, okay, is my unknown, okay? Because I want to determine, okay, the rate of the entropy generation, okay? This is my unknown. Now, I just solve for this, okay? This minus sign will be on the left-hand side as plus, okay? And this I have here, you see, 0.44. This is attention now, you see, this is H, in this case, this is S2 minus S1, okay? Now I have 0.44 here, okay? This is minus, see here, minus 0.02. Now on the right hand side, okay? Now jumping to the left hand side will be plus 0.02. This is 0.46 kilojoules, kilogram, and Kelvin, okay? So this means that the process does not violate the second law of thermodynamics, since the generation of entropy is greater than zero, is irreversible, okay? This is just an observation, okay? That's for you to see here. See? Q dot divided by M dot, just for you to see the unit, okay? Q dot is kilojoule by time, okay? By second. M dot is the mass flow rate, okay? Is mass divided by time. You cancel the time, you have kilojoule by kilogram, okay? Now, you see the rate of entropy is kilojoule by Kelvin by second. The M dot is kilogram by second. You cancel second, it will be kilojoule by Kelvin by kilogram. Okay, just for you to understand. Okay, how did I get this term over here? Okay, now let's erase here because don't confuse this term here. I just was explaining. Don't use degrees Kelvin. Okay, no. Then that's it. That's a problem. Okay, that's a reversible process. Okay. Now I'll show you the figure which I didn't mention. Okay, here I have the superheated vapor. Oh my goodness. Let's put it here. Here I have this point over here. Okay, let's put it here. This is superheated. Okay, you see the data 400 degrees centigrade. Okay, if you add here 273, you'll be 673 degrees Kelvin. Okay, and high pressure. Okay, the pressure here is high. Okay, this is a 30 bar, and the temperature T1 is equal 673 Kelvins, high temperature. Okay, this high temperature. Okay. This corresponds, okay, to 400 Celsius. Okay, and the temperature down here will be 100. Okay, from the data. Okay, now you see. Now that's important, very important. That's why I didn't mention this figure. Okay, at the beginning, because you see the entropy. Okay, increases. Look, from 1 to 2. Okay, look, you have the entropy. Okay, the process is not isentropic. Okay, because this is 2 prime. Okay, now from 1 to 2 prime. Okay, it's 2 prime. The process is isentropic, but in the real world, okay, you have increased the entropy. You had increased the entropy. Okay, this is at point 2. This is S2. This is S2 prime. Okay, which agrees with the result. Okay, so you generate entropy. Oh, look, that is interesting, okay? On this process, okay, from 1 to 2, okay, this process, the entropy is increased, okay, due to irreversibilities. Okay, that's very good. You see? That's why I repeat again. That's why I showed this figure at the end of the problem. Okay, that's it.